Right now, as you watch this, a machine built before the personal computer went on sale is still awake in the dark, more than 25 billion kilometers from the chair you are sitting in. It is about the size of a small car, it runs on less than half the electricity it launched with, and it loses a little more every year. By the time its voice reaches Earth, the signal is so faint you need a dish the size of a building to hear it, and it arrives about 23 hours late. And it is still reporting a measurement that our best models said should not be there. Nothing anyone built and no message from anyone else. Something quieter and harder to explain. A faint, steady tone in the emptiness between the stars. A sound that, according to the physics we packed for this trip, should have been far too weak to hear. Voyager 1 has been picking it up since 2017. Nobody realized it for 4 years, because it was buried inside data everyone had been trained to read as noise. And that tone is only the first of 3 things out there that do not fit. The instrument that found it has been reporting something else that still has no agreed explanation. The space beyond our solar system is getting denser the farther out we travel. Not thinner, denser. That is backwards, and 2 spacecraft, at 2 completely different points on the boundary, measured the same backwards thing. There is a third anomaly, the strangest of the 3, and I am holding it until you have the context to feel what it means. It is the measurement that made a generation of physicists look at their own models and admit the universe had not read them. And there is a clock running on all of it. As of this month, July of 2026, Voyager 1 has 2 working science instruments left out of the 10 it launched with. 2. And by a coincidence, almost too neat to be true, they are the exact 2 that found everything I have just described. At the Jet Propulsion Laboratory in California, engineers are attempting something they nicknamed the Big Bang. If it works, the measurements continue. If it does not, the sound stops. Not eventually. Soon. So let's go back to where this started, because none of it was supposed to happen. In the late 1960s, a few people at NASA noticed something on a chart. Jupiter, Saturn, Uranus, and Neptune were drifting into an alignment that only comes around about once every 176 years. Line a spacecraft up correctly, and it could use each planet's gravity as a slingshot, stealing a little of that world's orbital motion and flinging itself onward to the next. No extra fuel, just geometry and patience. They called it the Grand Tour, and then the budget arrived and cut it down to something modest. 2 spacecraft, 1 flyby of Jupiter, 1 flyby of Saturn, 5 years of design life. That was the entire promise. Look at 2 planets, take some pictures, go quiet. Voyager 2 launched on the 20th of August, 1977, and Voyager 1 followed on the 5th of September, on a faster path that would let it overtake its own twin. Each carried 10 sets of instruments, 3 computers designed in the early 1970s with a combined memory smaller than 1 photograph on your phone, and a gold-plated record holding greetings in 55 languages, in case anything ever found it. What happened next is the part people remember. Voyager 1 found active volcanoes on Io, the first ever seen off Earth, and a faint ring around Jupiter nobody knew existed. Its close pass at Titan cost it any chance at Pluto and bent its path permanently up out of the plane where the planets live. Voyager 2 went on to Uranus and Neptune, still the only spacecraft ever to visit either. And then the mission was over. Officially. The planets were finished, except the spacecraft weren't. They still had power. They still had instruments. And they were drifting towards something no one had ever measured from the inside. The edge of the sun's influence. The sun is not just a light. It is a leak. It throws a constant supersonic wind of charged particles out in every direction, and that wind inflates an enormous bubble around all of us called the heliosphere. Every planet, every comet, every human being who has ever lived has spent their entire existence inside that bubble. The bubble has a surface called the heliopause, and it sits where the pressure of the sun's wind finally loses to the pressure of the gas between the stars. The models drew it as a wall. Cross it, and you're out. On the 25th of August, 2012, Voyager 1 crossed it, roughly 122 times farther from the sun than Earth is, and the wall turned out not to be a wall. The spacecraft found a layered, leaking transition instead of a clean edge with the 2 populations bleeding into each other across a region roughly the gap between here and Saturn. Solar particles were escaping outward past the boundary, and galactic cosmic rays were slipping inward past it. The edge of our solar system is not a shoreline. It is a tide line, wide and porous and constantly shifting, with the sun's own magnetic field apparently holding the door open in places. That was surprise number 1, and it was mild compared to what the density did. Think about walking out of a crowded room. The crowd thins. That is the intuition every model carried in. Outside the bubble, you are in the cold, sparse interstellar medium, emptier. The measurement said the opposite. The moment Voyager 1 crossed the heliopause, the electron density around it jumped roughly 40-fold. Voyager 2, 6 years later, measured a similar leap, closer to 60-fold on its side of the bubble. The space outside our solar system is dramatically more crowded than the space just inside it. Hold on to your sense of scale, because the word denser is doing strange work there. We are talking about roughly 1/10 of an electron per cubic centimeter. The emptiest vacuum chambers ever built on Earth are still about 1,000 times more crowded than that. Interstellar space is emptier than anything we can manufacture, and still far less empty than our own outer solar system. But here's the part that broke the models. They kept climbing. Voyager 1's density readings started rising in 2013 and kept rising until the middle of 2015. Then Voyager 2, on a different part of the boundary, heading in a different direction, measured the same rising gradient. 2 spacecraft, 2 headings, 1 pattern. Which means this probably is not local weather. It looks like a real large-scale structure just outside our solar system, and there's still no settled explanation for why. 2 ideas lead. The galaxy's magnetic field may drape over our bubble the way fabric settles over a stone, strengthening the field and driving an instability that pushes plasma away from the boundary. Or, simpler and stranger, the interstellar gas flowing toward us slows as it piles up against the heliosphere, the way traffic compresses at a bottleneck. Voyager 2 had one advantage its twin did not. Its plasma instrument still worked, while Voyager 1's had failed back in 1980, 32 years before the moment it was needed most. So when Voyager 2 crossed on the 5th of November, 2018, it could take the temperature of interstellar space directly. The models predicted 15,000 to 30,000 degrees. It measured 30,000 to 50,000. Astronomers had already measured the wider local interstellar medium from Earth at around 7,500 degrees. So the plasma immediately outside our bubble runs several times hotter than the plasma further out. The leading explanation is compression. Our bubble plows into the galaxy's gas, and squeezing a gas heats it. Our solar system does not float politely in the interstellar medium. It shoves it. It piles it up. It leaves it hot. We are leaving a wake. And this is where the story changes. Of everything Voyager measured out there, the most stubborn result is the one that got the least attention because it was never a discovery at all. It was an absence. Our sun's magnetic field gets dragged into a spiral by the sun's rotation, like water flung off a spinning sprinkler. The galaxy has its own field, generated by everything else in the Milky Way, and it points a different way. Every model, every simulation, every textbook agreed on what would happen at the boundary. The field direction would change. It had to. You are leaving one magnet's territory and entering another's, so the needle should swing. On the 25th of August, 2012, Voyager 1's magnetometer watched the field strength jump, exactly as predicted. The direction did not move. It stayed lined up along the sun's spiral, as though the spacecraft had never left home. For more than a year, serious scientists argued Voyager 1 had not crossed anything at all because the magnetic field insisted it was still inside. The particle data said out, the density said out. The magnetic field said in. Then, in 2018, Voyager 2 crossed the same boundary. Different distance, different direction, different part of the bubble. 6 years later, in a different phase of the sun's own cycle. The field direction did not move there either. 2 spacecraft, 2 crossings, 2 independent chances for the prediction to come true, and it did not come true either time. Stamatios Kremigas, who has been running one of these instruments since before most of us were born, put it about as well as anyone has. Nature, he said, hasn't read the theorists' papers. Nobody has a clean answer yet. The best current thinking is that the galaxy's field gets draped across our bubble so thoroughly that near the boundary it is pulled into alignment with the sun's own field, and its true direction only reveals itself much farther out than anyone planned for. Which means that after 14 years in interstellar space, Voyager 1 may still not be measuring interstellar space. It may still be inside our own wake. Think about what that implies. The sun's reach may be far larger than the bubble we drew around it. We have not left. We have only left the part we knew how to name. And to keep listening to any of this, a small group of people had to perform surgery on a computer 24 billion kilometers away, blind. On the 14th of November, 2023, Voyager 1 stopped making sense. The spacecraft itself was fine. It was receiving commands, carrying them out, pointed at Earth, transmitting on schedule. But what came down was a repeating pattern of ones and zeros carrying no information at all. Voyager 1 was alive and listening, and had simply lost the ability to say anything. The fault was in a computer called the Flight Data Subsystem, which packages everything the instruments measure for transmission. If it cannot assemble a sentence, the instruments can work perfectly and it changes nothing. Consider the constraints. You cannot touch it, you cannot see it, and every question takes 22 and a half hours to arrive, and another 22 and a half hours to come back. So one test costs the better part of 2 days. The engineers who built the machine had mostly retired. Some had died, and the documentation is paper from the 1970s. And the computer you are debugging holds about 69 kilobytes of usable memory, less than one photo on your phone. For 5 months, they got nowhere. Then, on the 3rd of March, 2024, they sent what the team called a poke. Not a repair, just a nudge, a command asking the computer to dump its memory and say something, anything, in any format at all. 22 and a half hours later, a reply came back, and it was garbage again, except a different flavor of garbage. One engineer recognized the shape of it and decoded it by hand. It was a complete readout of the computer's memory. They compared it against a readout taken before the failure. And there it was. About 3% of the memory was corrupted. A single chip had died. Maybe a high-energy particle from space had struck it, or maybe it was just 46 years old and finished. Nobody will ever know which. That chip happened to be holding part of the code the computer needed to do its only job. And you cannot swap a chip at 24 billion kilometers. So they did the only thing left. They took the code apart, hunted through the memory for empty corners, large enough to hold each fragment, rewrote every internal cross-reference so the scattered pieces would still call each other and run as one program, and freed up room by deleting routines written for a planetary mission that ended in the 1980s. On the 18th of April 2024, they transmitted the first relocated block of code, and then they waited 22 and a half hours out, 22 and a half hours back. On the 20th of April, Voyager 1 said something readable for the first time in 5 months. By that June, all 4 of its working instruments were reporting again. The team on Earth had diagnosed a hardware failure, rewritten 50-year-old software around dead memory, and healed a machine in interstellar space that no human being will ever see again. That repair is the only reason we can talk about the sound. The plasma team had lived with a problem for decades. To measure the density of a plasma, you can listen to it, disturb it, and the electrons ring at a frequency set by how many of them there are. Denser gas, higher pitch. Voyager 1 carries an instrument called the plasma wave subsystem, built to hear exactly that. But out there, nothing was disturbing anything. The only reliable ringing came when the sun threw a violent outburst, and that shockwave took a year or more to reach the spacecraft. So the density data was a handful of points, years apart. They were reading interstellar space by waiting for the sun to shout at it. Then a doctoral student at Cornell named Stella Koch-Ocker went looking through the quiet stretches, the parts between the shouts, the parts everyone had learned to treat as instrument noise. There was something in there. Faint, narrow, almost a single unwavering tone, and it never stopped. It had been running through the data since 2017, and it tracked the density perfectly. Her senior author, James Cordes, described the interstellar medium as being like a quiet or gentle rain. The implication is the real find. Voyager 1 no longer has to wait for the sun. The gas between the stars rings on its own, continuously, and the spacecraft can read its density point after point after point, across stretches we could never map any other way. It is the first steady, continuous measurement of the material between the stars, taken from inside it. That tone is what shouldn't exist means here, not impossible, just not predicted, not modeled, not expected to be strong enough for anything to detect. And it has been playing the entire time. Which brings us to this month. On the 27th of February, 2026, during a routine roll maneuver, Voyager 1's power dropped unexpectedly. Its generator converts heat from decaying plutonium into electricity, and it produces about 4 watts less every year. It launched, making about 470 watts. It is now under half of that, and the margins are counted in single watts. Another drop would have tripped the spacecraft's own fault protection, which shuts things down automatically and hands the team a long, risky recovery. So, on the 17th of April, 2026, they switched off the low-energy charged particles experiment after 49 years of almost continuous operation. 7 of Voyager 1's 10 instrument sets are now dark. 2 remain. The magnetometer, which measures the field that refused to turn, and the plasma wave subsystem, which hears the hum. The instruments that survived the triage are the instruments that found the anomalies, and that is exactly why they were chosen. Which brings us to the Big Bang. The plan is to switch off 3 devices that keep the thruster fuel lines from freezing and switch on 3 lower power ones that do the same job for about 10 watts less. 10 watts buys a year. They tested it on Voyager 2 through May and June, and Voyager 1's turn is this summer. If those fuel lines freeze, the spacecraft loses the ability to aim its antenna at us, and the mission ends mid-sentence. There is one more date worth knowing. In November of this year, Voyager 1 will pass 1 light day from Earth, a full day of light. Nothing humans have ever made has been that far away, and no successor is remotely close. Its 50th anniversary arrives in September of next year, and the team is openly aiming for it. When the Big Bang result comes in, and when that light day mark passes, we will cover both. Subscribe, and you won't miss them. One last thing. On the 14th of February, 1990, over the objections of engineers who did not want a camera pointed anywhere near the sun, Voyager 1 turned around. From 3.7 billion miles out, it photographed Earth, and Earth came out smaller than a single pixel, floating in a stray band of scattered sunlight. Carl Sagan called it the pale blue dot. 34 minutes after that shutter closed, the cameras were switched off for good to save power for a road nobody had mapped. The software that ran them was later deleted from memory to free up space, and the ground equipment that could have read the pictures no longer exists. Even if we wanted another photograph, we could not take one. That door is closed permanently, so this is what we have left. A magnetometer, a plasma antenna, and a gold record carrying greetings in 55 languages, moving at 17 kilometers a second through a galaxy that will almost certainly never play it. In about 40,000 years, Voyager 1 will drift within a light year and a half of a dim star called Gliese 445. And then it will keep going. It will outlast the language this was written in, and every institution that ever argued about its budget. But not tonight. Tonight it is still out there, in a place denser than it should be, hotter than it should be, and magnetically pointed the wrong way. Still listening, still counting electrons, still humming back the one sound nobody expected to hear. And somewhere in California, a small group of people are staying up late, doing arithmetic in single watts, trying to buy it one more year.